Welcome to qnawire.
For this problem, we'll draw a diagram of our spring in each position. So in position 1, which is initially, the spring has length 26 inches. This is from Pythagoras. In position 2, when the collar is closer to point A, the spring has length 12.5 inches. So first, let's calculate delta. Delta is the distance that the spring stretches in each case. We know that the undeformed length of the spring is 10 inches. So in position 1, delta is 26 inches minus 10 inches, which is 16 inches. The potential energy in this position, V1, we'll call it, is a half K delta squared. So that's the potential energy stored in the spring. And that's half times the spring constant, which is 15 pounds per inch, times delta squared, which is 16 inches squared. And hence we get the potential energy in position 1 to be 1,920 inch pounds. And so we can convert this to 160 foot-pounds. So now doing the same, for position 2, delta is equal to 12.5 inches minus the undeformed length of 10 inches, and hence the spring is stretched to 0.5 inches. The potential energy in position 2 is a half K delta squared. So that's a half. Again, K is 15 pounds per inch. Delta is 2.5 inches. And we square that. So we're left with potential energy of the spring in position 2 is 46.875 inch pounds. And this is 3.91 in foot-pounds. So we have the potential energy in each case. So here we have a diagram of our rod AB in positions 1 and 2. In position 1, the distance between A and the center of collar C is 2 feet. The system rotates with angular velocity omega 1, and C has V0 in the first position to be R1 omega 1, and component VR of the velocity in the first position is 0. In position 2, the distance between A and C is R2. The rod rotates with angular velocity omega 2, and C has components of its velocity VR2, and V02 is equal to R2 times omega 2. So from kinetics, since we know the moments of all forces about the shaft at point A are 0, this means that the angular momentum about A in position 1 must equal the angular momentum about the same point A when the system is in position 2. So let's write down what these momenta are. So in position 1, the angular momentum is IR omega 1, where IR is the mass moment of inertia of the rod times omega 1 plus the mass of collar C times V0 times R1. That's the contribution in position 1. In position 2, the moment of inertia, IR multiplied by omega c not omega c, but omega 2 in position 2, plus the mass of c times v naught, this is v naught in position 1, this is v naught in position 2, times r2. So the angular momentum is basically conserved for each position. So we can write this as IR plus MC R1 squared. We just replace V0, V01 times omega 1. And this is equal to, we did the same on the right-hand side. This is IR plus MC R2 squared, and the common factor is omega 2. So we just replace V02. And now we can apply our data. So our given data tells us that the moment of inertia of the rod is equal to 0.35 pound foot second squared. The mass of collar C, MC, is equal to its weight, which is 6 pounds, over G, 32.2 feet per square second. R1 is equal to 2 feet. R2 is equal to 7.5 over 12, and that's also in feet. The initial angular speed, omega 1, is 12 radians per second. So that's the angular speed in position 1. So now if we go back to our equation above, we can start substituting our values in. So what we get is that 0.35, we'll suppress the units here, plus 6 over 32.2 into 2 squared, all times 12 radians per second, is equal to, on the right hand side, we have all these values again, 0.35 plus 6 over 32.2 into 7.5 over 12, and that's squared multiplied by omega 2. So omega 2 is unknown. So we can simply simplify this equation and solve for omega 2. And we get omega 2 is 31.089 radians per second. So that's the speed of rotation, the angular speed of the system in position 2. And so this simplifies to 31.1 radians per second. And that's our answer for part A, the angular velocity of the rod AB. Next, we are going to work with the kinetic energy in both positions. So let's work. Now the kinetic energy in position 1 we'll call T1. So the kinetic energy T1 is equal to a half IA omega 1 squared plus a half MC VD in position 1 squared plus the contribution by collar C mc VR in position 1 all squared. So this is half mc and the component v naught squared plus a half mc VR squared in position 1. So we can substitute our values in here. So this is a half into 0.35, again we'll suppress the units, times 12 radians per second squared, plus a half times the mass of C, which is 6 pounds over 32.2 feet per square second, times V naught squared, which is R squared, 2 feet squared. I'll just suppress the units here. So that's 2 squared times omega squared, which is 12 all squared, plus 0. So in position 1, VR is equal to 0. And so this gives us a kinetic energy in position 1 to be 78.865 foot-pounds. So that's our kinetic energy of the system in position 1. Now we'll do the same for position 2. So in position 2, kinetic energy is T2, and this is a half IR omega 2 squared plus a half M VB in position 2 squared plus a half M plus a half MC VR in position 2 squared. And so again, we can substitute our values into this. So that's a half times 0.35, which is the center of momentum, the moment of inertia for the rod, times omega 2, which we calculated to be 31.089 radians per second, and that's squared, plus a half into mass of 6 pounds over 32.2 feet per square second. Again, we can just suppress the units here. Times V squared we can write as 7.5 over 12 in feet, so that's R, and we can square that, multiplied by omega squared, which is 31.089 radians per second, again that's squared, plus the last term is a half times the mass of C, which is 6 over 32.2 times VR squared, which is in position 2. So here we can solve for VR squared. So T2 is equal to 204.32 plus 0.09317 times VR in position 2 squared. So the principle of kinetic energy, or the principle of conservation of energy rather, tells us that the sum of kinetic and potential energy is conserved in both positions. So what that means is T1 plus V1. Remember, we calculated potential energies right at the beginning. T1 plus V1 is equal to T2 plus V2. So the mechanical energies are conserved. So recall that V1 we calculated to be 160 foot-pounds, and V2 we calculated to be 3.91 foot-pounds in the beginning. So what this tells us is that 78.865 T1 plus V1, which is 160, is equal to 204.32 plus 0.09317 times VR in position 2, which you wish to calculate, squared, plus 3.91, which is V2. So rearranging this, we can solve for VR, which is our answer for part 2. So VR in position 2 is equal to 18.13, and that's feet per second.